Hi everyone, and welcome to today's session, which is the third part of the session for a roadmap for AI. So basically, we are trying to envision how will AI be in the future. For the first week, we start off with the learning from experts using fixed rules, using some form of decision tree, decision flow chart, and then moved on to like supervised and unsupervised learning. And supervised learning is learning with labels, unsupervised learning is learning without human labels. All right, and after that, in the second week, we talked about memory and how memory can be used to augment systems to make them more adaptable. So in this final session, we'll be touching more on agents. What's an agent? How are they going to interact together in a multi-agent system? All right. And finally, we discuss about artificial general intelligence, super intelligence, and whether we can hit the singularity. So it's very futuristic here. A lot of things are not set out in stone. So this is pretty much anyone's game right now. So this is a recap for part one. In part one, the expert systems are basically you have observations interpreted by human experts. Oops, sorry, let me just draw something here. Interpreted by human experts. Okay, then they will go into rules. Okay, something like if else rules and so on, and then finally build a model based on the rules. So the expert will basically provide the model. Okay, but in supervised learning, we let the human labeled data provide the model. So this leads to stuff like neural networks, where you learn from data of like cats and dogs, and you try to do some feature prediction. Like you can devise all the features end to end. And then in this era, we have self-supervised learning or unsupervised learning, which is basically without human labels, just doing next token prediction. You can already learn stuff about the data. And these next token predictions are something like transformers. And this is very, very cool because this means that what you can do is you don't have to train on any arbitrary tasks. You can basically use this to learn anything. And when you condition on the task later as the context, it can actually perform that task. So this is the new era of flexible prompting. And this is all facilitated by self-supervised learning. Okay, so how then do we make this self-supervised learning or unsupervised learning better? Okay, we can actually use memory. Okay, memory is in the form of retrieval augmented generation and so on. But moving on, the kind of memory that is needed to do something more hierarchical, something more arbitrary and flexible, it needs to be not just in the input domain, which is like text or images. It should be done at every single level of the processing pipeline. So I'm very inspired by what Jeff Hawkins wrote in the Thousand Brains theory. So basically a multimodal inputs here. Each input here gets to process this is a coffee cup. It processes it in a different way, in a different latent space or different process in, sorry, let me just write this. Process in different, you process this in different reference spaces or different reference planes, different abstraction spaces or latent spaces. My favorite word for this is abstraction spaces. So like maybe in one space, you view the cup in like 3D, in another space, you view it in single color and so on. So there are different ways to view it. How it is learned, no one knows, all right? But the idea is you can view this in multiple spaces. And then as you process this sequentially, you might even do something very, very similar to what you do here in the traditional architecture, where you go from simple to complex, but it's not required. You can also process this in parallel. And at every point of time, each part of this neuron in the neocortex, in the cortical columns here, these all will learn a different model of the world, all right, a different model of the cup. Okay, the skin will learn a skin model of the cup and so on. And where does memory come in? Okay, memory comes in because in order to process all this, okay, this is not exactly in his architecture, but I believe that in order to enhance the architecture's prediction, you can actually use memory to augment. So if let's say you have seen a coffee cup somewhere before, okay, you might be able to like draw on past memories of other different kind of coffee cups. Okay, maybe one cup is like that, another cup is like that. You can draw various memories in order to enhance the kind of way you process your data. And this is done very much like in retrieval augmented generation. where you have different text chunks that you use in before your query. So I'm saying that retrieval augmented generation is the baseline. Okay, it's actually very simplistic. I believe this is done at every single level of the processing pipeline. I don't like to use the word hierarchy now because the processing pipeline may not have hierarchy. It just might be many parallel views, right? So the idea that my Discord group has come up with is a memory soup. So I have to credit a few people, mainly Richard, for coming up with this. Okay, he's not here today, but he came up with the idea that there could be multiple like abstraction spaces all in the same soup. Okay, there's no layer-wise hierarchical memory. Everything might be in the same soup. And the good thing is that each single layer, the processing could draw on the memory. So it's like if, let's say, your objective for the layer is something like how to drink from coffee cup. Okay, it might be at the top layer or maybe it might be at the bottom layer because it depends on the task. If your task is about how to drink from coffee cup, that will be at the top layer. Then you split into the sub goals at the bottom. If your task is something like I'm thirsty, what do I do? What drink do I get? Then the how to drink from coffee cup can be way at the bottom. But we don't really want the memory to just be constrained to that particular layer or particular pipeline process. Okay, I don't really like to use the word layers also because it may not be layers in the brain. Yeah. So each particular part of the pipeline, if you need to reference that particular task, you then take from this soup the particular memories in order to enrich your representations. And that's why I quite agree with this idea of memory soup. In the future, we will talk more about memory soup in one of the future sessions because I think this is like a very key path to AGI. In order to solve the memory retrieval and encoding problem, I think this memory soup is quite needed. Okay, so these are more or less the summaries for what has happened over the last 2 weeks. Any questions so far before I move on to the actual content for today? Okay, so let's move on. So one thing that I didn't manage to talk about last week, and since we have more time today, is about reflection. So this reflection is quite important for memories because not only do we want memory that is fixed and static, okay, like for example, if you can do like, for example, let me give you an example of state A to state B to state C to state D. Okay, let's say your memory is only, in your memory, you only have this A to B and maybe B to C and maybe C to D. So maybe A could be like you flick a light switch and then there could be various other things and then eventually the light bulb turns on. So, sometimes if you just store memory by like a certain time frame, you may miss out the long-term kind of connections between that. So if you can do your reflection, what you could do is you can come up with a memory that maybe is like that, A to D. And what this means is that you can form longer-term connections. Okay, form more higher level linkages. So I'm just going to give you the example that was in this generative agents and interactive simulacra of human behavior. So this is the 25 agents in the Sims environment. Who here has heard of it? Generative agents? Can just raise your hand. The paper about the agents in this. Okay, so David has heard of it. All right, Aras also. So this is the diagram that is used in the paper. And what there's this guy called Klaus Müller, who's a researcher. Okay, and basically what we do in the memory stream is we save in stuff like observation. Like every time Klaus goes to the library, and you have this observation, Klaus reading the assigned material, Klaus using the library table to do research and so on. So we can consolidate this into one meta level reflection saying that Klaus is interested in research activities. All right, then if you have different streams of reflection, like for example, in this stream of reflection here, okay, we have his daily plan. So you can see that his plan is in the morning, read the research paper and so on. So even his plan can form a reflection. All right. And over here is like, who is he interacting with? All right. And over here, you can also see that he is dedicated to research. So in this case, the reflection here tells us the same thing for all 3 branches, which kind of means that he's doing only one thing, which is research. And so we can even have a meta reflection branch here. Okay, so this is an example of reflection. What I talked about on the left just now is about time sequential reflection to do long range reflection. What this generative agents paper show is another kind of reflection where we do reflection over multiple kind of domains, over the plan, over the interaction with the environment, over interaction with people, and so on. You can have multiple streams of reflection, and the reflection is able to give us a better understanding of the world. And if we need to, we can actually use this reflection to do our predictive tasks next time using retrieval augmented generation and so on. Okay, so that's a very important use of reflection. And I would say that this is one of the key reasons why we dream. All right, so no one has really solved dreaming yet, but I believe dreaming helps to form this kind of long range connections and form this more abstract and higher level representations. So yes, David, you raise your hand. Yeah.
So, I mean, this is sort of encouraging an artificial reflection, but fundamentally, this is all still just being put into an LLM and being processed as if it were one large block of text. Even if there is sort of this memory store that's swapping out different prompts, there can't be a sort of fundamental speaking to oneself under this paradigm, right? Or did I not read the paper correctly?
Okay, so after you do the reflection of the basic level observations, this reflection can actually be used to do the decision making. So you don't have to like include all these observations anymore. When you do like your cosine similarity search, you can actually just take this reflection directly to solve the query. So in some sense, it is helping to do like some form of chain of thought, is it? Like because initially you needed all these three, right? But now I can just use my reflection to condition my prompt or condition my query, which in some sense it is an advancement in the kind of thinking. Like you don't have to have the low level representations anymore. You can just extract out the meta level ones.
I understand. Right.
Yeah. So this process of reflection, actually that's a good point. Yeah, it kind of mimics chain of thought, but we do this implicitly so that like at runtime we don't have to do chain of thought. At runtime we can just take out whatever we have learned from our earlier like low level representations. So yeah, reflection is important. But then again comes the question of how much to reflect. Okay, there's actually been neurology studies or neuroscience studies that show that some people spend too long reflecting. Okay, they have some brain lesions and basically they spend a lot of time thinking. So like even stuff like taking a remote control and choosing what channel to watch, that could take an hour. All right, so reflection is good in a limited sense, but as with all things, we shouldn't reflect too much. If not, you might just spend your whole day reflecting, and then maybe you won't get anything done. So reflection is useful. Okay, let me caveat here. Useful. Reflection is useful. Okay, but only do for pertinent events. Basically pertinent as in important events, because we don't want to overwhelm the memory. Okay, and we don't want to store too many reflections. Okay, because this might actually affect our like limited memory storage. Okay, so there are a few things to take note of when we do reflection. I think a limited form of reflection is useful and definitely helpful in terms of doing more and more advanced plans. All right. But we don't want to do it too much. So what's the threshold? We don't know yet. Okay, so to find out this threshold, I think this is something related to a topic that I'm not covering in this session, but I think it's very related to solving the problem of self-learning agents, is emotions. Okay, so how do we know when to reflect, when something is a very big thing or when something is a small thing? And I think the answer lies in how much emotion we feel about the event. Okay, so for example, if an event is very sad, you tend to store that memory more. All right, you tend to reflect upon it more. Right, if that event is very happy, all right, you may also reflect upon it like, yes, I'm going to try to do it again and so on. But sad will affect us more. Fearful memories will cause trauma. All right, and that causes you to reflect a lot on it. So people have like post-traumatic stress disorder and so on, because I think what I suspect is that the brain is trying to reflect too much on these events. You try to associate everything, and try to avoid experiencing it again. Yeah, so this emotional cues could be the reason why we reflect. All right, and there's also another one, surprisal. So imagine you have a doorknob, you open the doorknob every day. Suddenly one day the doorknob is at a different place. Okay, but because you do by instinctual habit, you access your memory, you try to turn the doorknob and the doorknob isn't there. It's like, hey, something's missing, something's wrong. Then you are like, oh, the doorknob has changed its place. All right, this is what Jeff Hawkins calls like, instead of like what we do in the current computing paradigm where we store everything in like vectors or like databases, key value. So for example, door, you would store like doorknob at this position and so on. So you can store like a million properties of that door. That's probably not how the brain does it. The brain probably does it differently. We can store certain memories about actions that we do, and then if it doesn't conform, the world doesn't conform to what we imagine it to be, we will be very surprised and we will update our memory of the world accordingly. So this idea of updating the memory is also related to reflection, because we reflect upon our existing memory and we change it. Okay, so this is useful for very dynamic systems where you want to keep changing the stuff in order to update it to match the world environment that keeps changing. So I would say that a huge part of learning how to adapt comes from emotions. All right, so this means that I probably should do another session on this, because I myself feel quite strongly about this. I think emotions are very important in terms of how humans think. Now, recently there's a paper called emotional prompting. So apparently, if you can do stuff like at the end of your prompt, say this line like you do your prompts, and then you at the end you say this is very important for my career. All right, you try this and you get more accurate responses from the large language model. Okay, and I tried it. It kind of works for some cases, not all. Okay, so this shows that in the training data of text that LM uses, it already shows the cases of emotions being involved in it. Like if you were to write something like that on a forum, maybe you get more accurate responses from other people, because people will be trying to help you with your career. Rather than if you don't put this, then it's like they might dismiss it as just any random question. So emotions are very important for humans in order to focus your attention and effort too. And I believe this is also very important in the reflection process as well. Okay, I'm going to stop here for a while. Anything you'd like to discuss or add on to this slide? Okay, if not, I'll move on. Okay, so this is quite important, right? So this reflection will be a huge thing, okay, as we get to self-learning agents. We haven't solved this problem yet, but we will soon be able to solve it. All right, next, agents. All right, the big hoo-ha about OpenAI and so on. What are agents and what are multi-agents? So this from Lilian Wan, one of the OpenAI researchers, I think more or less summarizes what agents are currently. All right. So of course, I think there's more to this, but let's just talk about what people think agents are right now. So the agents are currently like a large language model system, augmented with some memory. So this memory here is something like your text chunks and so on, your text chunks that you split up and you do like embeddings and so on. This are the memory, or like conversational histories. Yeah, so there's a few things that you can store here for memory. Planning skills. What are the planning skills? Chain of thought. Okay, chain of thought are stuff like let's think step by step. All right. So, reflection. Reflection is good. It's like reflect on your answer and correct your mistakes. So this is in the paper reflection. Yeah. So you can see that reflection helps quite a bit. Okay, it actually improves their soft rate of this environment called ElfWorld by close to 40%. Yeah, which is remarkable. Okay, so there are other stuff as well. Sub-goal decomposition used by stuff like AutoGPT, MetaGPT, and so on. Yep. So, actually, I'm not sure whether MetaGPT uses it. I have to check again. But AutoGPT, okay, definitely uses this. Like you split a goal into sub-goals. Self-critic, you can ask the LM to critique itself. It's actually similar to reflection. This is used in cases like Voyager. Voyager has a critic whereby the LM will give a critic back in free-form text, and the agent will use it to plan better code. So Voyager is the one that is the agent that basically can solve a Minecraft environment, right? So what else are there in agents? There's one very important thing, is called tool use. So tool use is stuff like this: calculator, calendar, search, and so on. Why do we need tool use? Okay, maybe I open the question to the floor. Why do you think tool use is needed for an agent? Anyone? Okay, you all don't have to be shy. Okay, I will continue. All right. So tool use basically is used because LMs are still fundamentally stochastic. All right. They use the next token prediction over some probabilities, and you sample those probabilities, right? And they are not very well used, not well suited for consistent generation. So if you need stuff like consistent generation or rule following, or basically you just want to augment it with other capabilities like images, voice, and so on, search maybe. Yeah, you use tools. Okay. So calculator, LMs are not good at math, I can tell you that. All right. Calculators are way better. Code is better. Yeah, you can use tools as code as well. You can do code interpreter as one of them as well. So this helps to augment the limitations of large language models and give it better things so that it's able to do more things. Right. So I do think this agent framework is very promising. It's much more promising than the multi-agent architectures of the past using reinforcement learning or using some very complicated domain-specific language that's not as free-form as large language models. So this paradigm of agents is a very nice one. All right. And yeah, what else would I do to improve this? Probably to make the tool use learnable. All right, but we have a question from David. Yeah, please go ahead.
So this is very centered around language models. Do you think that this would change if we start using multimodal models or other modalities in the mix? Like, is there pros and cons to weighing that?
Yeah, I think if you use multimodal models, the underlying method to learn the multimodal model will likely still be a transformer-based method because unsupervised or self-supervised learning is very powerful. You can generalize across tasks quite well. So maybe you can change your agent to a multimodal agent and you can process the stuff. However, there's a disadvantage of a multimodal agent like that, is interpretability. All right. If you use a tool such as you can use a image QA tool here, image question answer, you might be able to get more information about your image. Okay, but if you use the multimodal agent and you give image tokens at the start, okay, you have image tokens, and then after that you have text tokens. So people have tried to do this for architectures like Blip, BLIP. Yeah. So this is the text tokens here, image and text. You might lose out on what the image token does because your response is is unlikely going to be in the form of an image for the agent. It's likely going to be in the form of text. So I would say that multimodal agents are useful, but in terms of this agent wise, you may still follow this structure more. Okay, there could be image used in the processing pipeline in the agent itself, but I'm very sure there's still going to be tools to explain those images. Did I answer the question?
Yep.
So this is more or less the start of what agents can do. In the agents video I also shared what are the things that can be done more. I think you can also learn your own skills. Okay, you can also maybe have a dynamic memory. Okay, because I think you do need to learn from the environment. You can also do something else, like your agent itself actually can be still trained. All right, can be still trained more. Okay, but this one is a slow process of training. All right, you can see more in my learning fast and slow. You have a neural network that can still update based on the environment. But in order to learn fast, you use the memory. Okay, so this one I just presented last week. I see there also. So this thing is you have both a neural network, which is this agent itself, and the memory itself. This tool itself, you can get fast learning. And then as your memory, you forget more and more stuff, the capabilities get transferred over to the agent itself. Okay, so this is more or less the overview of the agents. What are the examples of agents we can see right now? And here we have the most hyped up thing of the last week, which is GPTs. GPTs are your own custom chat GPT. You can add in your own prompts. Okay, you can add in what tools it uses. Okay, basically it's like a code interpreter, some RAG. You can basically give it your own documents also. Okay, but based on the comments I've seen on LinkedIn, if you give it your own documents, people might be able to retrieve it with some prompt hacking. You can do it. So be careful if you use it. All right. And then also some action spaces it has. So it's like it can even search. Okay, so maybe it's part of tools as well. So yeah, tools it uses. Yeah. And yeah, so basically you can customize your own agent in some sense. Okay. So what is lacking in this ChatGPT agents? Okay, these are great stuff in order to do very simple things. But you can see that if you look at the diagram on the back here, it's missing quite a lot of things. Okay. It does have a bit of memory because you have RAG and so on, but it's missing the learning part. Okay, it doesn't learn. It doesn't learn from inputs. Okay, unless you put it in the memory. Okay, so this one doesn't really have it. Okay, it doesn't interact with other agents, at least as of now. Yeah, I tried to create multiple agents. It said it couldn't interact. Okay, so there's a lot of things that are missing in the GPT's framework. Okay, you can't really customize this process yourself that well. Yeah, you can't really do this. A lot of things in agents, you need to do some form of rule-based plus LMs because the LMs cannot do everything. Sometimes your rule-based will help you to give some behavior already without using the LMs. And that part, I don't think you can customize that easily with GPTs yet. So there's a lot of things that are missing in this. Great first step. All right, great first step. Have you all used this before, by the way? Any of you have used it? GPTs? Okay, so maybe this is still quite new. Yeah, you can try to use it. You realize that it's pretty much just like I would say a useful assistant. Yeah, it doesn't really learn from what you do and so on. You start a new session, everything is gone. So this is a very basic implementation of agents, and definitely not the future. Okay, I can see this being like maybe this will be like the okay. We talk about compilers, all right. This might be assembly language of compilers. Okay, we haven't even got to like Python yet. Yeah, so there's a lot of things that are missing in this entire framework. Right, so I'm going to talk about how we can possibly implement multi-agent framework using like large language models, or in the future, it could be other models. But in general, it should be a self-supervised or unsupervised learning system so that it can learn freely from all sorts of data. Okay, so I'm not exactly advocating LLMs must be always there. The architecture can change, but the fundamental property of self-supervised learning using some form of next token prediction should be there. All right. So what are the things that we can do? So let's take a look at the first thing over here on the left. So again, I'm going to use a Numenta example. So this is from hierarchical temporal memory. Okay, but really, if you look at Thousand Brains theory, this is similar as well. You have different fingers. Each of them have a different model of the world or different part of the object. Okay, and what happens is that each of them will have only know a certain thing, but at the end of it, they do some form of voting. Okay, that basically they consolidate all the information together. So this is very, very similar to like having multiple not so smart agents, each of them doing their own stuff. Okay, but a consolidation of all of them eventually will give you the full picture. Right. So this is what I like to call multiple sampling and filtering. Okay, mark my words, all right? This will get us to AGI. All right. Multiple sampling and filtering will get us there. Okay, why? Why will it get us there? Okay, before I talk about why, let's talk about the architecture that I have in Learning Fast and Slow, the model I just presented last week. So this basically saying that like if you want to get from a start state, like A, to a goal state, maybe D, okay, we sample through memory starting from A. Okay, we go through memory, we come back, maybe we get state B. Then we go through memory, we come back, we get state C. And then we go there and back again, we get state D. Okay, eventually you have your full pathway from A, B, C, D here. That you basically, you can sample out the entire trajectory and play it out. So this means that you can sample multiple ways, and maybe over here, this gets stuck in a loop. Yeah, and doesn't reach the goal, but it doesn't matter. As long as one of these branches that you sample reaches the goal, okay, and we just take the first one that reaches, the fastest one, which is likely the most optimal. We take this branch here, and then we do a form of lateral inhibition here. So after the first one reaches the goal, we do lateral inhibition, and we block out all the other paths. Okay, so this in some sense is multiple sampling and filtering. We sample multiple pathways, or like we kind of visit the future multiple times, and we just choose the best path, right? And why is this multiple sampling and filtering useful? Okay, the same thing for the cup. You also sample multiple times, and then you filter out the best hypothesis out of all the votes. Why is this useful? Okay, and I would say that it's useful because, all right, you don't only have one way to solve a problem. Okay, there can be many ways. Okay, so we just try out multiple variations. Okay, but all these variations must be something that you have learned over over your experience. Okay, because you cannot just come up with something that you have never done before. Okay, that's not possible. You have to reference something. Okay, and then by choosing the best method, okay, you can then back propagate or update your memories accordingly. So in some sense, this is a self-improvement method, because you filter out the best answer, the best hypothesis. This can be used to update your model and train the model again. Like we can train the transformer again on, given a certain query, what is the best output? Okay, can you see this? Yeah, so this can also be applied on transformers. You sample 100 or 1,000 responses, rank each of them by a human or by a reward model, if you like reward models. Use that best answer and do supervised fine-tuning. All right, and that can improve the performance of the language model already without RLHF. Okay, so anyway, that's my gripe about RLHF. I don't really like it because RL is very slow to learn. All right, so this is and RL doesn't generalize out of the training distribution. That's very important. Okay, so this multiple sampling and filtering, by sampling multiple possible paths and choosing the best one according to some metric, you are ensuring some form of improvement in that metric you are measuring. Okay, you may not get the optimal because you are not sampling across all the pathways, because that's impossible to do. But at least in the pathways that you sample, you can choose the best and you can train the model on the best one already. So this multiple agents, multiple sampling and filtering, I believe is the path to achieving AGI because of this idea. Yeah. So that is the kind of thing that I would like to emphasize. A lot of things that we can do right now are basically in this kind of idea, right? Multiple sampling and filtering. This is what we can do with multiple agents as well. Within the same system, what can the agents do? They can do this. Okay, any questions for this? All right, so there's also another way to view multiple agents within the same system. So this is what I did in the ARC challenge, the abstraction and reasoning corpus, whereby I actually achieved about 45% solve rate on 111 problems, which is more or less the world record so far for solve rate. Right. So this is the idea that you don't only have one abstraction space to solve your problem. Like some problems in this. So anyway, to give an example of those, for those who don't know what's the ARC challenge, it's a 2D grid with a certain number of squares. Okay, it can be like 3 by 3 to it can be 1 by 1 to 30 by 30. So let's say you have a number of squares here, and then maybe your input relation is like that. You have a red square, and the red square shifts 1 square to the right. Okay, so it can be a red square, it can be a red object, and so on. The thing is, the computer doesn't know what is the rule. It has to infer from a few training examples, typically 3 training examples. And then it needs to apply this rule to the test case. So it's just like an IQ test for computers. Supposed to be very easy for humans, but very difficult for computers to process. So what did I do to do it? I basically give it the various rule-based views, like grid view is the whole grid. Object view, I extract out all the objects in the grid. Pixel views, I basically just give it the color of each pixel based on the coordinate system. Okay, so based on all these views, I asked LLMs to then like generate the rule and then generate a program, a Python program to implement the rule. And then what I do is I do a filtering step. This filtering step will basically check which program works on training set. So this basically says that I have various ways to process my data, and I can process it using different agents. Each agent can view the world in a different way, in a different abstraction space. One is grid view, one is object view, one is pixel view, and so on. And also each of them have a different, could also have a different action space. So like maybe one agent is can do things in grid space, one agent can do in object, one agent can do in pixel space. I haven't implemented this yet, but this is in the works. Okay, so if we can constrain the action space for each agent, we can also get very unique generations from each of them. So earlier on, you saw in the previous slide, we have the same agent. Okay, now we have different agents doing different things. And we take their output all in a common space here. So this is the common space that the agents will output in. And then we do some form of voting. So this is another way that we can get multiple agents within the same system to work. Okay, and this is very powerful because this allows you to solve a problem at different levels of hierarchy or different levels of abstraction. You know, because sometimes you don't want to solve the problem at maybe the pixel level because you might be dealing with objects. So you want to solve at object level. Sometimes you want to solve at the entire grid because you want to rotate the whole grid and so on. So this is very, very crucial. A lot of systems right now only have one abstraction space or one latent space. Okay, and this means that you are limited in the kind of things that we can do to generate stuff. You know, like stable diffusion, they do it in the latent space, right? Then when you back generate to the pixel space, sometimes you have 6 fingers or 4 fingers. You know, the finger issue about generative AI. And that's because they don't have conditioning on multiple spaces. They only have conditioning on one space, which is the latent space itself, which may not remember that, you know, a hand has 5 fingers. So stuff like this highlights the importance of existing systems to have more than one abstraction space in order to process information, so that the information that is processed can be more diverse. And then we choose the best one for the task because we don't know the task beforehand. Yeah, so all these things, I think is very exciting. I would like to see more research work done on this because I actually haven't seen anyone else do this. I'm probably one of the first few to do this. I believe this ties in very well to the idea of memory soup. So the last session I talked about memory soup, and memory soup is basically you have memories of multiple abstraction spaces. So all these things could potentially reference the memory soup and use that for enriching their representations. So it works hand in hand. So I'm very excited to get some form of memory soup out, all right, to get some form of these multiple specialized agents out, because I think it can solve quite generic problems. All right, anything to add for this? All right, if not, let's move on. So another interesting thing to talk about for agents is, can we learn the skills from the environment? So here I show you the diagram of the Voyager. Okay, Voyager is the Minecraft agent that tries to learn things by itself. Okay, of course, it has some knowledge base of the Minecraft Wikipedia. Right, so there's different tasks. The automatic curriculum learner will basically diversify the tasks and also based on what has failed and what has succeeded, try to give a task of the right level for the learner. So after the teacher comes up with the task, like maybe in this case, we want to do a combat zombie task. All right, it basically will be able to consult like the knowledge base of like what kind of things need to be done first, like some what are the prerequisites and so on. So all this the knowledge base would have. Okay, and then it comes up with a JavaScript kind of bot that can be used to play in the Minecraft environment. So this JavaScript bot has a very interesting thing called skill retrieval, which I like a lot because the skill retrieval allows you to use your past code that is stored in a skill library. And you can basically use the code. For example, if you have a stone sword crafting, all right, you can actually reference your stone sword crafting code in order to craft a stone sword here. You can also craft a shield over here. Yeah. So all this you can use your past experience of doing various things to craft certain things or to do certain prerequisites. And then you can use that in your new code here to basically combat the zombie. So if let's say you don't have the stone sword and you don't have the stone shield, you know, you go and craft it. If not, you can use this straight away. So it allows you to do more complex tasks by composing earlier tasks. And how do we know when to add in this task or when to add in this skill? Okay, when the environment says, yes, we have solved it, we add in the skill here. So basically, we will be able to do more complex tasks as we progress through the environment. And of course, and succeed at tasks assigned. Yeah, because if you don't succeed, okay, what will happen is you need to keep refining your program until you succeed. And what will happen is you may not have this skill in your skill library. Okay, but this is an interesting framework because this allows us to learn new tools. Okay, in this case, tools are in the form of computer programs, right? Which are great actually because computer programs are more consistent than large language models. All right. So you can learn new tools, new skills, and this is very useful in order to gain more competency in your environment. And you realize all this are done, all this learning is done without backpropagation. So who needs neural networks to backpropagate when you have memory? And skills or tool use is one such memory. And if your agent is able to learn how to use tools, it's able to do more and more complex things. And this is something that I think needs to be researched more because this is quite key for self-learning agents, right? We don't want the agent to just learn with their base network. We want it to augment, we want the agent to augment more and more memories. Actually, I consider this skill table as memories because you can learn more and more things from this memory and use it to do decision making in the future. All right. Okay, yes, Prince, you raise your hand. Yeah. Anything?
Yeah, to understand how this skills is different from memory soup. Is there some different structure that is used to store this skills?
The skills are stored in the JavaScript program, which is like basically this program that is created here. If the environment says that we have succeeded in the task, all right, then we will just update this. So basically the environment means like GPT would actually say that yes, succeed or not based on the environment details. So it's a self kind of verification. Yeah, so
Okay, so,
this skill here is the code itself. Yeah, so maybe you could have a large language model to generate code to generate like, I don't know, prime numbers. Then basically the one code can be generate the fifth prime number, one is the six, one is the seven, one is the eight. Then you can just keep adding the new code here. Yeah, so in this case, their skill library is code.
got it. So you just choose one and just code block and run it, and it should solve that particular task.
Yes, yes, correct. I mean, you can do this for leak code also. Your your prompt could be solve a leak code. You can use it to solve a leak code problem. And then your output here could be the solve leak code problems. Okay, I mean, it do not need to be leak code. It could be like, I don't know, coder chef or something. Basically, different kinds of problems. And then once you have a new problem, you can reference so when they saw the skill library, I didn't show it here, but they also have a summarized description of the skill. And then what they do is they do embedding here. And then what they then do is from the query over here, or the task, they also do an embedding. And then they find the top k nearest neighbors to augment. So they don't augment everything. They find the top k neighbors to augment by cosine similarity. So in some sense, if we do this, you can actually learn more and more skills and hopefully use what you have learned earlier if there's some synergy to learn something more complex later on.
Does the LLM who is incorporating all these things needs to be fine-tuned to use skills, memories, and other things in a specific manner, or prompt engineering is enough in that case?
Okay, good question. So it's only good enough using prompt engineering if the training set already has stuff that can solve the skills. So one of the key things why code works, because we have a lot of code stuff. GitHub, LLMs train on a lot of code. So it's able to do some form of coding quite well. But if you wanted to do stuff like, I don't know, math, reasoning, yeah, you may not get the answer. And like ask it to solve math theorems, okay, no, I don't think that's going to work. Because one bad thing about this method is that if you cannot solve the task, you don't learn anything. Okay, because there's nothing updated in your skill base. Okay, you can possibly update that, yes, I did not solve it. But in cases like in reinforcement learning where you have a sparse reward, like for example, you have a person over here. This is a grid world. You're a starting person here and your door is here. Okay, maybe you explore every single part of this world, but you never reach the door. The agent doesn't know how to solve. Okay, so in very difficult problems, like if you wanted to win in chess against a chess master, there may not be a very straightforward answer because it requires like a few hundred moves before you can see your answer. In such cases, like you use reinforcement learning or you use this kind of method, LLM, to prompt the next move and so on, it doesn't really know how to solve it. And in that case, it may not learn. So what this means is that in order for learning to continuously happen, okay, your curriculum needs to be well structured, or if it either needs to be well structured or you must be able to learn something from any environment. So one thing that I've done in like learning fast and slow is you can make any endpoint. If you can make any endpoint your goal, you can actually learn start point to end point. So I go one step further for learning fast and slow. I say I not just learn from start point to end point. I learn from any point in the trajectory to any point after that point. So I learn from all combinations of start to end. So if you are able to frame your problem as an arbitrary start point to end point problem, okay, maybe like move from XY to maybe move from coordinate 3, 4 to 7, 8. Even though it did not kill the zombie and so on, at least it learned how to do some stuff like moving. So that could be a way to learn something even though you have failed in your task. Yeah, so something like this is not done in the Voyager architecture, but that could be done in order to learn from stuff. And then like eventually, as you learn how to get from certain point to certain point, you might be able to find maybe this path here. Yeah, so I think something like that could be looked into. But right now, for learning of skills, right now, only the successful skills can be learned. So we kind of need to make the skills more learnable, easier to learn, so that like even if your LLM doesn't give you the answer, you can still learn something. Then maybe you might be able to offset the training bias of your LLM. But honestly, in my opinion, if your LLM is not trained on something similar to your data, it will not be able to solve the problem easily. And I do think some form of fine-tuning is still needed to the environment. Yeah. Minecraft works because Minecraft is mainly code, and Minecraft is mainly natural language. Like you say, make crafting table. I mean, it's quite obvious what make crafting table is in language, right? Combat zombie is quite obvious. But if I change this combat zombie to like if I were to just change it to something like that, ASDJFKL zombie, I'm very sure the language model may not know how to generate the right code. Yeah, Prince, did I answer the question?
Yeah. Thanks.
Yeah, great question. So this highlights the importance of being in the pre-training data or being in the fine-tuned data for the large language model agent. If you go beyond the training data for the agent, its cognitive abilities are not good. I've tried it out on a few agents of mine, asked it to do some escape room, and I need to prompt it in the form of a language that is familiar with, which is like semantic language, English. All right. If you do it in some arbitrary symbols, it doesn't work that well. It doesn't do the pattern matching that well. So do take note, if you use LLM agents, it needs to be in the pre-training distribution as much as possible. What is in the pre-training distribution? Basically text you find online. Yeah, you try to match the semantics there for better performance. Okay, I'm gonna move on. All right, I'm gonna move on. All right. All right, collective intelligence. All right, so this is something I'm very interested in as well. I last held a book club session at Machine Learning Street Talk to talk about collective intelligence. This is the idea of how multiple people can come together and share their knowledge so that as a group, the group becomes more well-informed. can solve better problems and so on. So what are the examples of collective agents intelligence right now? Again, the one that I talked about most recently is ChatDev, which is basically a procedural method to generate programs to like simulate a software development company. So you have a designing phase where your CEO will come up with some idea based on the query. The CTO will give some technical suggestions of how to implement it. Okay, maybe you have a product officer as well that iterates. So how they did this was just iterating it like that. One will be the person who wants the task done, and one will be the assistant to get the task done. So, you know, when you talk to OpenAI, you are the instructor and OpenAI is your assistant. Over here in this framework, both are AIs. Okay, the instructor is an AI, the assistant is an AI. They talk to each other and they continue going down the chain. Okay, as they go down the chain, they like get modality, which this information will be passed down to the agents of the later parts of the chain and so on. Language, these are meta information that will be passed down to the chain. So there's some form of hierarchy here. There's some form of process-based conditioning. So like the later processes condition on the outcomes of the earlier processes, which I quite like a lot because that's more or less how we kind of break down a tough problem into simpler bits, right? Your simpler bits, like for example, if I want to go from point A to point B, maybe it's very complicated. What I will do first, like I said, I will go from point A to point C with a taxi and point C to point B with a ferry. Then like what action do I do? Like for taxi, I need to book a taxi. For ferry, I need to find a ferry terminal. I need to, you know, go and book the ticket and so on. So the action spaces will be conditioned on the earlier parts of the process. So I quite like this idea of this process-based conditioning. I don't quite like the idea that you only have one agent talking to another agent like that. I mean, that's not exactly the way things are. Sometimes it's groups, you know, this doesn't have this kind of framework. It's not, this group framework is not there. And also sometimes you make the decision in your own brain. You don't need another agent to talk to. Like you do realize that meetings are very lengthy and meetings take time. You know, Elon Musk like to say cut out all the meetings, all right, that are not useful. So sometimes as you look into this ChatDev agents, they talk a lot of nonsense, right? They don't really talk. They are not to the point. Okay, and I would attribute that to RLHF because RLHF likes to give you a bit more nuanced responses and so on. Yeah. So this idea of having multiple agents talking to each other is something interesting. But maybe conversation is not the best way sometimes. Okay, so there might be better ways to transfer knowledge. Okay, so I'll talk about how to do this later. But sometimes you can just decide on your own. You know, sometimes deciding on your own is enough. So how then do we know, okay, when do we do collective, when do we do individual? Okay, this is an open question, all right? If you can solve this, you can solve a huge chunk of AGI as well. Like how do we know when the individuals form a group is better? How do we know when not to? And what are the motivations for joining a group? Yeah, I believe it's all done at the individual level actually. The individual must find some match to the group and join it. And the moment that they don't find any match, they leave the group. So this needs to be modeled in. Okay, so let me just write this down somewhere. Model process of how groups are formed, how agent decides which groups are important, and so on. So actually, I did have an idea of how I'm going to look at sociology text to find out how groups are formed in history and so on. I just haven't had the time to look at it, but I'm very interested to see how we form groups, like how cells form groups and so on. So all these things play a part in collective intelligence, where once they form the group, we will share the knowledge among the agents. So the other example I'm going to talk about is this generative agents. So basically, in this case of generative agents, they infuse the starting state of one agent with the idea that one agent wants to hold a Valentine's Day party. So apparently, that's the only agent that knows. But through the interactions of the agent with another few other agents, they spread the knowledge. Okay, and this is an era without social media. So it's like mouth to mouth. And eventually more than half the agents turn up for the Valentine's Day party, which is impressive. Okay, because it means that like just one person has an idea, it spreads and spreads and spreads. Like maybe I have some idea, I go through the YouTube and it will spread. So collective intelligence of how to share knowledge is something quite fundamental for intelligence. All right. I always like to tell people, if someone is in a deserted island, it's very unlikely that computers will have been born. All right, because computers, you need all the microprocessors, you need electricity, you need all the electronics. It's very hard for one person to invent everything by himself or herself. So through the sharing of knowledge, through building upon each other's knowledge, we grow as a species, and humans evolve in knowledge and so on. So collective intelligence is a huge thing for AI. And if we can model collective intelligence, we can model self-improving behavior. Okay, it's quite important. I'm going to repeat this again. If we can model collective intelligence, we can model self-improving behavior. Okay? Because agents can build on each other's work, and then they can incorporate into their own knowledge, and they can improve themselves. Okay, that's the ideal. Of course, as you already know from like maybe your own personal experience, if you are belonging to some group that doesn't benefit you, sometimes you might be worse off. Right? You might get influenced negatively and become a worse person than you join. So it's not all like roses and great stuff to form groups. So this is something that needs further study, right? And so I think cross-disciplinary studies would help, because group forming has been done a lot in sociology and also in biology, like cell forming and so on. All right, anything to add for this? Right, it's a cool idea because we now think of agents not just as agent itself, but as a group of agents talking to one another. And that's very, very interesting. So how do we do this knowledge sharing? All right. So this is a very, very interesting idea. Like, how much knowledge do agents share with one another? Because you don't want to share your entire knowledge bank. Okay, let's say this is agent A and agent B. We have some memory that the agent has experienced. Maybe at night, the agent sleeps and reflects upon it. And then we also have a meta memory that is of a higher level, which is like maybe after being processed in the pipeline. Again, this is not a reflection. This is just like after processing the memory down the pipeline or processing, there's another higher level memory. Like maybe in this case, this is like go from point A to point B. And then like the other memory down here is like buy a ferry ticket. Okay, I mean the meta memory might actually be a more specific memory, because if you talk about broad actions at the lower level, the later levels will be more specific actions. Okay, so if we have another agent here, and over here maybe it's like buy a train ticket, and over here is go from point B to point C. Right? If we have a navigation problem and both agents are of the same type, same abilities, if we want to share the knowledge with one another, we can just say that, hey, I don't need to communicate with you, right? Why communicate when I can transfer you the memories directly? Right? Why do I bother to communicate, right? I can just I use some ESP or some way of brain waves to link to you, and I can just give you my entire life's worth of knowledge. Okay, would that be better than a conversation? So next time, if you need to go from point A to point C, okay, if you need to go from point A to point C, you already know, okay, because you already know that you need to take a ferry and a train, all right, because you can consolidate both memories together. Right? Sounds great, right? And shouldn't we want to download all our experiences to one another? Right, there's a problem with this. Okay, anyone want to tell me what could be the problem if we download all our knowledge to one another without any filter? Anyone want to try it? What's stopping me from having a system of agents and they all share their knowledge together, everything into one, like a hive mind?
Very large context first thing is there, and I think agent can also get confused because of too many things.
Very, very good. Yes. So that's exactly the kind of thing I have in mind. So why not have a hive mind where too much memory may be given, okay, and then your memory may be irrelevant. Okay, so when is a hive mind useful? All right, a hive mind might be useful if all the agents are experiencing the same environment. And then it could be treated as multiple ways of exploration, and then you consolidate all the experiences back to one person. That's fine. I think if in the same environment is fine. But if your environment is at Atlanta, I'm in Singapore, you share with me your knowledge, it's just going to overload my memory system. Something like retrieval augmented generation, it works well if there are few documents to retrieve from. But the moment you increase the number of documents, your retrieval might fail because it gets confused, or it kind of thinks other documents are relevant when it's not. So if you download too much memory that's irrelevant for the agent, you end up having poorer decisions made by the agent itself. So you don't want to share everything. You just want to share stuff that are relevant. So we should only share things that are relevant to the agent. Right? So perhaps we don't have to do it by communication. Right now we do by communication because we cannot directly plug into one another's minds. Okay? And actually communication is a slow process. Like for example, in order for me to share with you the knowledge that I wanted to share about agents, it takes 1.5 hours. Right? If I can plug my brain directly to yours, maybe we could get this done in 1 second. Right? But yeah, I mean communication may not be the best form. Okay, but communication allows us to, say what's important to each of us. Like if you say that, oh, I'm not interested in this, maybe the conversation can stop there. Yeah. So these are stuff that I think could be done in a faster way than conversation. Right now we use conversation for like chat dev, for generative agents. But because these are AI systems, you see, we don't have to follow humans. We can just do the hive mind concept. But we should do a limited hive mind concept because not all memory is important. And some memories, especially memories that are not related to the agent, will harm the agent. One more thing, memories that are linked to actions that agents cannot perform, right? Like let's say you are an acrobat, you transfer to me your knowledge of how to do backflips and so on. I try to do a backflip, I might end up with a broken back. All right, so you don't want to do stuff like that for agents with different capabilities. You may not want to share information that much because you may end up doing things that are harmful to the agent itself by trying to imitate that. Yeah. So yeah, this reminds me of another thing, like how humans learn. All right, we don't only learn from conversations. We also learned it through this thing called imitation learning. Right? How many of you here have kids? Anyone? Yeah, I have a kid.
Yes. Yes.
Yes. Okay. So do you realize your kid imitates you a lot?
Of course.
Yes, correct. So imitation learning is one of the key ways humans learn, okay, especially before language is learned. So if let's say you like to, suck your thumb a lot, they will learn from you how to suck your thumb, okay? If you like to do other things, like for example, you like to curse a certain word, eventually they will keep cursing that word as well. So imitation learning is very important for learning because the state space of actions is so wide when we are born. There's so many things that we can do. But what are the good things for the environment? So kids learn from adults because adults have survived from the environment. Okay, this is my theory, of course. There's no reason why things happen in nature, right? Everything is just like that. Okay, but if we were to give a reason for why kids did do imitation learning, it's like this. Because adults have survived in the environment, they should already have things that are useful for surviving. And so imitating this action should be useful for the kid. Right. So imitation learning is maybe one way to transfer this motion memory from one agent to another without conversation. And actually it's a very efficient transfer. Like kids learn very fast from imitation learning as compared to telling it them in words. Like if you imagine you tell them, hey, no eating of the things that drop on the floor. Hey, no doing this. I have a kid, I try doing, and then the kid will just like maybe take two to three times before they learn something. It's not obvious, but if you do it by action, actually it's way faster to teach them. Like if you drop a lollipop on the floor, you throw it in the rubbish bin directly, they might learn the action. So yeah, that's something that we have to have in mind about imitation learning. And for humans, imitation learning works because the action spaces are similar. All right. So to conclude this slide, knowledge sharing between agents is quite useful. It helps an agent learn beyond its lifetime's worth of experience. You can consolidate past experiences, parallel experiences of multiple agents, and so on. But the agent should have the same action space. and the agents should have the same environment. Okay, we shouldn't let the agents learn stuff that are irrelevant for them. And as a final filter, maybe the knowledge that are shared should be related to the agent's personal environment. Because maybe everything, like let's say we are all in the same earth, but we may be living in different conditions. There's no point in me learning how a life is like in Atlanta if I'm not going there. So that is an example, okay, of how an agent should only take in stuff that are relevant to itself. Okay, how to know what's relevant? Maybe you can condition on past life context and so on. Yeah, and also there's one other thing about memory, let me just erase this. Our own personal memories are not perfect records of things that happen. It's actually malleable. And this, I attribute it, this is my hypothesis, is that we change memories to update them to current context. So if we have this in mind, yeah, of course you may disagree with this hypothesis, but if we reflect upon the memory and if we think about our current life, like all your childhood memories might slowly transform to like where you are right now, like based on the location and so on, you might adapt it. In fact, it might not even look like it's adapted, it might look like the real thing. So people often have false memories, right? But they are still useful, okay, if they can help you with your decisions in the current environment. So given that our personal memories are not perfect, okay, of course in AI, we may want them to be perfect because we need accuracy from the AI. But just taking some insight from nature, maybe when we share knowledge, right, what will happen is if we still have this system of malleability, you may feel like the other person. All right, you basically, like after you learn the knowledge through a download like that, you may behave like the other person. Okay, like I don't know if you have done counseling before, but if you counsel someone and they tell you a life story, sometimes you might feel for them, you might feel empathy and so on. And like after a while, it might affect you because the feelings still come to you, although it's not your life. So there's a problem if we just share knowledge like that. You might behave like the other person, especially if the other person has very, very traumatic memories and so on that affect the emotional circuit. You may not be able to behave properly. So one other thing to note is maybe you only want to take in memories that are similar to what you already have done. Yeah. So I don't have any answer for this, but this is a word of warning, caution. Oversharing is not good. Right? But sharing for some things are useful, but oversharing may not be a great thing. Okay, this is a very interesting slide. Anything else to add before I move on?
Hey, John, sorry, I kind of joined late. I'm not sure if you covered this question already. So when knowledge sharing between agents and they will share like in a memory one and memory one, what's the relationship between meta memory and memory? Because we talk about the memory soup. So do agents have direct access to each other's memory soup, or is one share in a big pool?
Correct. So this one, basically meta memory is like some build on of the memory, like in the sequential process. Like the memory could be going from point A to point B. The meta memory is like buy a train ticket. So it's like a more specific outcome of the earlier memories. In this case, you can treat each agent as having this is the memory soup for each agent. If we were to treat the memory soup framework, each memory soup is distinct. It's not shared between agents. So now we are discussing how much of the memory soup to share. And I'm saying that sharing the memory soup is useful if the action spaces are the same for each agent and the environment is the same. But it may not be useful if you have two different environment. And also, even if in the same environment, sometimes you share too much, you might lose out the personality for each agent, you see? Like you might feel like the other person based on your emotional circuits and so on. So and it might even affect our own personal memories because like it's malleable and so on. So the thing is memories make up who we are. If you just take memories like that, you might lose out on personality. But as AI agents, you may not need them to have a personality, right? So this might be still okay. But I'm talking about like for humans, if we have this capability, we may not be ourselves anymore after we get the memories of others. Yeah, so I'm just discussing. These are like closer to philosophy already. I mean, we don't have an example of how this would pan out.
Oh, I see. Okay. So you might also will cover this later on slides, but so the question is, I really enjoy the white paper that you sent us, on the voyage on Minecraft, right? And they generate actually a Python script. So would it make sense to just to share the Python script of particular memory, like actionable memory, instead of just directly sharing memory, but sharing the Python script might give us direct access to exactly what the agent will do in a certain context.
Yeah, it's possible that the memory exists in the code as well. But as with all things, code, you have code injection. If one agent is a virus, you might share a virus code to another one, and then the other person will break down. So it is possible to share knowledge in like a Minecraft agent via code, definitely. But then it comes with another set of problems. Which code is useful, which code is not. Yeah, so that is unsolved. Yeah.
Sure. Okay. Thanks.
Okay, so Ara said the AutoGen libraries added some support for integrating with OpenAI GPTs, might help with experimenting some of these ideas about explicit knowledge sharing. Yeah, definitely. So if you have multiple agents that can share a common pool of memory, yeah, I mean you can get closer to this kind of framework of knowledge sharing. But again, we need to be very careful about what is useful and what is not. If all agents are doing the same tasks and you only share, this is something that only share the best. I think that might be helpful, all right? Because this is something like mass sampling and filtering. You filter by best performing agent. So your agents will become better and better at the task, and then the best agent will share its knowledge with everyone. You can treat it like, some Nobel Prize laureates. Like they have a very good idea, they get recognized, and everyone goes read their book, learning fast and slow and so on. Yeah. So thinking fast and slow. Learning fast and slow is my idea. So thinking fast and slow is like the idea by Daniel Kahneman, and like he's quite well acclaimed, and people read it and understand about stuff. So it could be like you share knowledge based on certain criteria, like it must meet a certain threshold before it shares to everyone. Because the moment you share the knowledge, it kind of contaminates everyone's minds. so, so that's a very good point. This system might work. This best knowledge sharing, it might work, but it might lead to very specialized agents. Okay, which may not be as adaptable as someone new. Okay, so this touched on another point that I hold very strongly to: why we die. All right, I believe that as we gain more and more knowledge like that, okay, it's not that we become less plastic in our brains and so on. We just have more memory and we have more baggage. We may not be as adaptable as a young kid who has no idea of what's good and what's bad. They might be able to adapt better to an environment because they don't have that kind of emotional baggage or memory baggage. Yeah, so while we can share knowledge, we must be very careful that we can still have new agents in the environment so that when the environment changes, these new agents can take over. Can learn new things to adapt to the environment rather than just learning what has been done in the past. So interesting topic, a lot of philosophy here. I'll leave the discussion for another time because I do have some more slides to continue. All right. Maybe you should have a book club session on this, on machine learning street talk. Yeah. So let's continue this next. All right. Doing one population may not be enough. We need more. All right. We need more populations. Sometimes just debating about like how one population will turn out to be, like in generative agents, you only do one snapshot. Yeah, it only provides you one snapshot of what can happen. So if you are talking about multi-agent interaction, sometimes you might want to simulate many different snapshots. So you can simulate out many different possibilities using multi-populations. Okay, over different conditions, maybe, yeah. So this one maybe is useful to help you to find out what conditions are useful for your population. Like if you are doing city planning and so on, like SimCity, you can simulate many different events. You can also simulate many different outcomes of a certain interaction because everyone has certain stochasticity in interactions and so on. So you can do this simulation and then you can basically choose the best conditions over multiple populations, right? This is useful if you want to do population level simulation. If you want to do like maybe individual level simulation, maybe you just need to simulate them in the same environment, right? So this is what can happen if we have enough compute to not just simulate an entire population, but simulate multiple populations. Of course, you can go beyond multiple populations, you can multiple universe and so on. Yeah, but I stop at multiple populations because I think this will be complex enough already, right? And what's the usefulness of this? Okay, the usefulness of this is that you can optimize in changing environments. Okay, how? Again, we go back to this idea, right? And this is the idea that I say will lead us to the AGI. So mark my words on this. Multiple sampling and filtering. Okay, so AGI can be summarized in one sentence like that. Multiple sampling and filtering. Okay, I believe very strongly in this. Like all my architectures are based on this. And this has gotten me to improve on the model's performance just by itself, right? Multiple sampling and filtering. You sample multiple instances of what could happen in the future and you choose the best one. Then you learn from the best one and so on. Yeah, you can keep doing this and your model will keep improving to a limited extent, right? So let's move on to the really interesting discussion. Can AGI be achieved? All right, so we talk about all this population, knowledge sharing and so on. Can we achieve artificial general intelligence? Right, so this is a huge topic, one that will normally take days to discuss, but I'm just going to condense it because we are not going to talk too much about this, all right? It's still a bit of a hazy thing, but one thing for sure, we can define AGI and ASI, artificial superintelligence. Why define it in both ways? You will see why later. AGI is better than average human across all tasks. ASI is better than best human across all tasks. Okay, why are they different? Okay, the thing is average human, right? We can actually do imitation learning. And this is something like what a transformer is doing right now. Okay, you can just learn from the data that's online, and then that will be better than the average human already, because the data online is usually input by like less than half of the world's population, and usually are the more literate ones. And so if you can learn from data online, you should be better than the average human already, right? Across all tasks is a bit too much. Across all tasks that are text-based, all right, that may be one way of doing it, because LLMs learn based on text. Okay, so right now, AGI for text-based, I think we have achieved it already, because we can have large amounts of training data. You ask LLMs to write a code, sometimes it writes better than most people. Right? It writes better than me, definitely. I'm not a very expert coder. Okay. I think it also does poetry better than me. I'm not an expert poetry as well. Yeah. But I mean, in terms of envisioning what kind of systems that are useful for AGI, I think I do better than the AI, because AI spots a lot of nonsense. Okay, so there are things that the AI or math also can do better than ChatGPT for most of the time. Yeah. So there are some things that an average human may not have access to because of limited lifetime. You only experience so many things. The AI, like ChatGPT, has access to so much data. It's like multiple lifetimes of data that's available. It's able to beat the average human across many domains already. Okay, you have to admit it. The ChatGPT is better than you in more than 10 domains. Okay, if not, you wouldn't be using ChatGPT much. Okay, so this AGI, I would say, for text-based tasks has been achieved. However, if you talk about all tasks, no. Okay, what are the kind of tasks that we cannot achieve AGI yet? Okay, locomotion, robotics. Okay, because all these are difficult. All these require data of how to manipulate the world, how to interact with the world, and there's a lot of noise in the world. It's not as clean as text data. A lot of difficult problems, and most importantly is because we are doing reinforcement learning. And I would like to highlight here for all the reinforcement learning fans, reinforcement learning is a very bad way to learn from data. It takes very long. All right, those who say RL is good haven't used RL yet. Okay, RL is a very slow way of learning, right? And that's why I came out with learning fast and slow. Okay, because learning through memory, learning through goal-directedness rather than rewards is a much faster way of learning. Okay, it's so fast that in the learning fast and slow, my fastest method achieves like 92% solve rate compared to like PPO, which is proximal policy optimization, a solve rate of about 61%. So it's like at least 30% improvement. Like on a bigger environment, like 40 by 40 is like the PPO only solve it 4% of the time. I think mine solves about 40%. I can't remember the exact percentages, but reinforcement learning is very slow to learn and adapt. And that's probably one of the main reasons why it's not, we haven't achieved AGI for that area yet. We don't have the right system to do self-supervised learning. So I do believe self-supervised learning is key to AGI, because you want to learn from any kind of data. You don't just want to learn from labeled data, and you also don't want to learn from reward signals. It's too slow to learn. Okay, that one, another session again. That will take too long to explain. Right. ASI, artificial superintelligence. Can we do it? Okay, the answer is no. Not yet. Okay, but maybe you can say, but for like maybe chess or Go, like compute intensive. Yeah, maybe. Yeah. So artificial superintelligence means that we can no longer imitate. We need to improve upon the best data available, right? And this cannot be done through self-supervised learning alone. Self-supervised learning only learns from the data. If you want it to go beyond the data itself, you need some form of self-improvement, all right? And this form of self-improvement is not natural in the self-improvement coded separately in the system. So this self-improvement, what was the phrase that I was talking about just now about how to achieve AGI? Multiple sampling and filtering. So I do think if you can just do multiple sampling and filtering, you can improve upon the stuff that you have learned through your self-supervised learning, and you can also through multiple agents, because multiple agents will get different experiences and so on. You can pick the best one. You can also use basically the idea of memory to condition generation, okay, in order to limit the search space. Yeah, you can do all these ideas, and of course with multiple agents it's okay to limit the search space for one agent, because you have so many other agents who have unconstrained search spaces. So multiple sampling and filtering across a single agent, across multiple agents, maybe across populations. If you can do this and the compute scales up, we can achieve ASI for domains that already have self-supervised learning, right? Of course, you might say chess and Go, where's the self-supervised learning here? Okay, chess and Go is a unique case, right? They have self-play, okay, because the game is symmetric. You can learn from the winner. Yeah, so chess and Go are special cases of stuff that don't really need self-supervised learning. Okay, but actually in self-play, it is some form of self-supervised learning, because there's no human labels here. You are learning from the ground truth, which is like win or lose, right? But if you are talking about like other stuff, I don't know, motion tasks, yeah, maybe you could have self-play, I guess, like you can see which agent walks the faster, then we learn from that. Yeah, but I would say that that's more related to multiple agents. Yeah, so once we get this multiple agents framework solved, how to use this memory for different agents, how to get different agents to share memory with one another, we can perhaps achieve ASI. Yeah, I wouldn't say this AGI, ASI cannot be achieved. I would say AGI, we have achieved it for some domains already. ASI, with the right self-learning framework, using multiple agents and memory, we can achieve ASI. Okay, so sounds a bit scary, right? But I do believe we can do it. Okay, so let's open to discussion, because I think this is a very interesting slide. Kai asked, does ASI always require data? I would say yes. You need data in order to find out what's good and what's bad. Okay, you cannot just base ASI off a heuristic. Hi, yep. So we are back. So just now I was saying that the artificial superintelligence can be better than us, because what happens is that although the human brain will need some energy and effort to do stuff like math, ASI will likely not need all those, because they have compute. They are not restricted by compute. So they are able to simulate the various future possibilities based on their memory. And basically this can already outsmart the best humans because of this one word that I was sharing just now. And this word is very simple. It's called multiple sampling and filtering. So I believe you can do this at the single agent level. You can do this at the multiple agent level, and you just infuse this with your memories of past experiences. That can already achieve ASI. And yeah, I was answering the question about whether ASI needs data. I would say that yes, it needs data, because without data, what will happen is you will not have the kind of basis in order to tell what's best. So the data and also some environmental feedback will be needed to create your ASI, right? So this can be even accelerated faster if we could create accurate simulations of the world, right? Like what we do in video games. And then we can already create, like, even in games like Gran Turismo. Let me just go write this, Gran Turismo. The AI keeps playing the same game again and again, and they are able to get the best performance that beats a professional player of this game. So Gran Turismo is like F1 racing game that simulates the realistic physics of the world. So we can create something like that. You can have your agents play those worlds, and you can find out the best agent through simulation and hopefully adapt it to the real world. And one bad thing about stuff like what we are doing right now is we're still using RL methods, which can be brittle and like too focused on one environment. So what needs to be done is we can also, like, people have varied the environment, like varied environment and so on. You could also have, like, instead of RL, you can I don't know, you can use population based methods to select stuff. Yeah, so this basically gives some idea of, like, when environment changes, you can adapt. Right, so there are various ways we can do this. I think all these have been explored, and all these are very, very crucial to achieving artificial superintelligence, because we need this diversity, we need the filter, we need the sampling, and we need the filtering. So all this, if this multiple sampling and filtering is done, regardless of how we do it, by memory, RL, you can also sample multiple times. I just don't like RL because it takes too long to train, but RL is possible to do this as well. Like, basically, they managed to do it for some Atari games and some static games, sure. But the moment we have dynamic environments, RL is out of the window, right? We shouldn't use RL for dynamic environments. It takes too long. Should use some stuff like population-based methods, memory, and so on. So I would say it's very fascinating because we are almost halfway there already. We have, through the use of transformers, achieved AGI for tasks that are text-based, for most tasks that are text-based. Okay, we just lack the kind of data for robotics tasks and locomotion tasks and interaction in real world kind of tasks, which is a difficult problem, right? And we haven't solved one thing. We have yet to solve vision. Okay, because, like, if you want to talk about vision transformers, they take away too much info. Okay, so maybe what we can do is we can have multiple abstraction spaces. Or maybe you have VITs. I mean, if you want to use VITs, I guess I can still buy it right now, because I do think the Retina comes in various patches now. But we can have VITs at multiple patch scales. Yeah, we could do something like that. So once we have solved vision, we can solve a lot more things for robotics. And then we can soon solve most of AGI. Okay, but for ASI, you need way more compute to solve it. Way more compute, because you need to sample multiple times and filter them. Yeah, I pause here for maybe 5 minutes. Anyone wants to add on?
So I have a question about, like, why it's possible, why is required for ASI, why we need so much data for ASI. Isn't it possible for existing AGI systems, like, for example, ChatGPT, to generate its own data sets for getting to ASI? Because the reason I have this intuition or thinking is basically, what's the human equivalent of ASI? It's like, basically, like, for example, a new branch of philosophy or a top researcher at the cutting edge where he has no data to learn from, right? And he pushes himself to the equivalent of human ASI, which is basically he's better at that field than every other researcher by creating his own data. So that same thought process I'm thinking is it not applicable to existing systems for LLMs?
You're saying that the LM can create its own training data and basically
Correct. And
do
then
the sampling and filtering by itself.
correct. Yeah, the sample filtering will obviously have to be based not on itself, but on other types of ground truth. Perhaps using it to predict certain like experiment, but using that itself to generate the data, I think might be a more scalable way, because as you have mentioned just now, it's way easier to get data for average human text, but for ASI it'll be a lot harder, right? Because of, I mean, it's just more rare.
And also you may need to outperform the best also. So you cannot just rely on the best data.
Yeah, exactly. Yeah.
Yeah,
So why can't it generate its own data? That's my question.
I agree with your philosophy. In fact, this is also part of multiple sampling and filtering. You can use the LMs to do the multiple sampling. Okay, however, you cannot just use one LM or one agent, okay, because the agent might be biased. So if the agent is too biased, it may not be able to get the solution, the best solution, or get a better solution. So what may be needed is you need to have diversity. You need to have multiple agents doing different things, and then you can generate all of the like multiple sampling through various agents, and you just filter based on the best agent. And like how we filter, maybe you go through some ground truth by the environment. Like for Arc Challenge, it was whether you can solve the training set, right? So this, I mean, for grid line environments is like whether you reach the goal or not. So, or like the furthest distance you travel. So you can have some form of filtering heuristic, and you can learn from multiple agents. That will say ASI can be done. You cannot. I strongly believe ASI cannot be done with just one agent alone, because one agent has limited experience. The stuff that it generates, although you can use temperature equals 1 or higher temperature, the stuff it generates is still limited by its pre-training data or by its biases. Yeah,
Got it.
So on that topic, this is a nice segue to perhaps to say that diversity is good, right? Because if you don't have like, diverse perspective from multiple agents, you really cannot advance your knowledge. Is that correct?
Yes, just one single agent itself, especially if it specializes through its lifetime, you lose out on the adaptiveness. And that's why we need new agents, new perspectives, and so on. And I mean, you can also see this in academia, like the old ideas are reigning because like a lot of people believe in them because the majority of the researchers are like of that particular generation. And so new ideas get blocked, right? So this is something that also happens like if you specialize too much, okay, you may not be as receptive to new things. And so in order to find a better answer, sometimes you need to remove your prior assumptions and do something different. And that's what I'm trying to do with RL. I'm trying to say reward is not needed. Okay, so I'm trying to remove that assumption there. And people use Markov decision processes. I'm trying to say that no, we don't need this. You can just use memory. So stuff like this is things that highlight that just one single agent is not enough to do improvement. You kind of need to improve as a group.
Agree. Okay. So another question is the vision. So vision here, are you saying that like, you let the robotic to have a vision to look at the real world, say, say for example, like, self-driven cars, or you're talking about like in Minecraft, the agent is traveling in a simulated world? Because in a simulated world, you don't really actually need like robotic vision, right? Because the simulated world, those objects are actually like codes, right? The agent can directly interpret instead of like actually looking at the simulated world like in Minecraft. Am I correct?
Yeah. So sorry, can you repeat that again? Your agent doesn't need to look at the code.
So in a simulated world, say for example, in a virtual world, right? Either in Minecraft or in like NVIDIA's Omniverse, right? So when you see an agent in there like trying to play and create like stone or diamond tools, the agent can actually interact in a simulated world without actually using vision, because in a simulated world, those objects are just programming codes, right? They're not actual objects that require robotic vision. Is that correct?
Yeah, I mean, for environments, if you can put the environment into text-based, you may not need vision. Yes, but for most generic cases, we still need vision because we may not get the information in text if we don't use that vision input itself.
No, I mean like in a Minecraft situation.
Minecraft,
so
you may not need vision. Yeah, Minecraft, the text of the environment might be enough.
Okay, I see. Great, thank you.
Yeah. So anyway, this ASI and AGI thing is quite interesting, and I do think we can achieve ASI within our lifetimes. Okay, what I don't think we can achieve is the singularity. Okay, and what is the singularity? Singularity means that ASI system can continually self-improve all the time, keep improving and improving, and it becomes like the source of truth. It knows everything. Okay, my answer is no. All right, clear cut, no. I don't think singularity can be achieved. All right. So why? Because if you want to keep improving, you realize it's getting harder and harder as you are already very good at it. Like for an expert pianist to improve on his piano skills, he has to learn way harder. You know, like the 80-20 rule. You spend 80%, or sorry, you spend 20% of your time mastering 80% of it, and then after that, that's it. Then it takes exponentially longer to get more and more mastery. Like if you look at the AlphaGo or AlphaZero ELO chart, it goes like that and then it tapers off like that. So it takes very, very long in order to improve the ELO rating again. And this shows that in order to improve on something that you are already very good at, sometimes you might need to like lose your prior information and go to a branch that's not explored. And this kind of things are hard to find. It's not very obvious. It's not a continuous search space. So that's why you might need multiple agents to do that. And while I say multiple agents may achieve us ASI through multiple sampling and filtering, may search more, may be able to search more. But this is still limited to the search space. Yeah. So if your search space is a lot compared to the number of agents you have, then you may not be able to self-improve anymore. All right. So of course, if you say you have infinite compute, then yes, I suppose you could reach the singularity because you can compute all outcomes. Yeah, but I don't think that's realistic. So I don't think we will hit the singularity because we will not have infinite compute. The second thing is that dynamic environment changes means that you need to relearn most of the time. And in relearning, you kind of have to go down in terms of what you can do and then go up again. So self-improvement based on your previous environment is not likely. You need to keep adapting and learning in new environment. And that's why we won't be able to like hit this point whereby like is the best all the time because there's so many different environment changes that could happen. Your best right now is different from the best later on. So with this in mind, I don't think we will hit the singularity. You have anything? Any thoughts on this?
Yeah, so that is correct if we let AI to run towards singularity as an autopilot. But it's got to be some point where the human factor comes in, where the human intuition can also guide the AI. Perhaps we can approach singularity closer than just autopilot by the AI. Do you think?
I guess we can hit closer to the singularity, but I don't think we reach a point where we will be better at all times. Yeah, so my point still holds, like we still need to change based on the environment changes. So I really don't think we'll hit the singularity.
Right. But what do you think is the role of human like injection at some point that can help and do things that ASI would not be able to do?
I think in the case of ASI, we must already admit that ASI is better than us at all regards. So because they might learn using the same mechanisms that we learn, but they can learn at a much larger scale. So it's like humans playing chess. Like we might think that okay, we have reached the pinnacle of chess, but then the AI system like AlphaGo comes in and say, or AlphaZero comes in and say, hey, there's a better move. So if let's say AlphaZero cannot find a better move by itself, it's very unlikely that humans can actually find a better move because the way that we do the search space traversal is much smaller than what AIs could possibly do. So I don't think humans can actually guide the AI to reach singularity. I mean, we might get it in the architecture, but in terms of what it learns, I think it's unlikely. If the ASI system has not figured it out, it's very unlikely that humans can actually figure out how to get to singularity. Okay, so anyway, this is a debatable point. No one knows for sure. Okay, but my view is no. All right, so I'm just going to move on to the last part because it's quite late already. I'm just going to cover like 5 minutes what I think these questions are. So first question is related to the data. Like there's only so much data that can be learned that are good. After that, it needs to improve on its own. How is that done right now? Right now it's still through self-supervised learning. And I guess in some sense doesn't really improve. But as what I've been saying, we can actually use the multiple sampling and filtering in order to select better options and in a more like multi-agent manner with memory. And you can perhaps improve by just using these multiple agents to explore more of the environment and pick the best one. Use the memory and also conditioning on your memory to generate better responses. So this I think can be done. Okay, this can get us quite far, right? Will compute and larger models solve the problem of self-improvement? Yes, to a limited extent. Because they provide better search traversals. Yeah, so you can do your sampling better and filtering better. But if your agent doesn't learn how to improve, it will, no matter how much you search, okay, it doesn't solve this problem. So you need to have the agent exploring the right part of the environment, which compute alone may not be able to help. You need smarter ways to search. Yeah. And maybe that's something like AlphaGo. Yeah, they use this kind of Monte Carlo tree search. Yeah, something like that is, if you look at Monte Carlo tree search, essentially it is multiple sampling and choosing the best one. So we have gotten that algorithm right. Multiple sampling and filtering. We have gotten that right in some systems. We just need to scale it up more. Next, should we do planning based on hierarchy? If not, how should hierarchy be learned or constructed? Otherwise, how to plan? So I think hierarchy is useful. Wait, let me use a different color. So I think hierarchy is useful for certain tasks. Like for example, vision. Like you need to relate the objects to each other and so on. Yep. But other tasks, you might just use multiple abstraction spaces that are not hierarchical. And yeah, can hierarchy be learned or constructed? The thing is, it depends on the situation. Sometimes it can be learned, sometimes it's constructed. Like constructed in the case of like, for example, you have a country and a city and a state and so on. All these are like fixed hierarchies that are man-made, but we use that for guiding our thinking. So in this case, it's a constructed hierarchy. But hierarchy can also be learned. How is learned? All right, how is hierarchy learned? It could be learned through experience. Like for example, you can chunk data together, chunk frequently occurring data together for hierarchy. That's one way of doing it. You can also do like hierarchy can be learned by reachability, like basically like how frequently co-occurring are end states. Okay, so this is very related to the first idea of like how the data occurs together. So I mean, recently at ICDL, I met this guy who talked about reachability, and I quite like this idea. So he might be coming over to give a talk on this soon. So it's basically saying that based on how states can be linked to one another, you can construct a next level like state space. So instead of like state 1 to state 10, at the next level could be state 1 and state 2. So state 1 links to state 2, state 2 links to state 1, and so on. So hierarchy could occur based on what we experience in the environment, and we group like commonly occurring things together. That's one way to do it. The other way to do it is to based on the human construct. There's also one other way of doing it, which I don't like. You can also learn hierarchy through end-to-end learning, like for example, convolutional neural networks. But this hierarchy is not exactly that great because it need not really be a right hierarchy at all. It's not exactly like low level is ages and next level is objects and so on. It could be just random noise, which is what I observe most of the time. So you could learn end-to-end hierarchy. Yeah, it's just not exactly going to be that great. Okay. All right, let me just do the last two, then I'll just ask if there's anything. So next we only have unsupervised learning for textual data. How can we do unsupervised learning for vision motor as well? I think we need to solve the problem of self-supervised learning for vision and for agentic behavior, like interacting with the environment. So right now, we have vision transformers, but they are not self-supervised yet. iJEPA is trying to do it, but they are not doing it like next frame basis. So we don't have this thing yet. Agentic behavior, RL currently doesn't do self-supervised learning. But you can take a look. I'm trying to get this out using learning fast and slow. I'm trying to do self-supervised learning for agentic behavior. So once we get this out, we may achieve ASI or AGI for these domains. All right, last question, also a quite important question. How can we simulate multiple environments if we do not have an accurate enough model of the world? Okay, so this is a very important question because like when we talk about multiple sampling and filtering, we kind of need the environment to be suitable enough or realistic enough for this filtering or sampling process to take place. So if we don't have this good environment, okay, what will happen is we will have very lousy predictions of the future. So how can we simulate this? We can't. So what we can do is we can approximate using past memory as baseline, but it will not be accurate. But the thing is, if it need not be accurate for it to be useful, but it may still be useful because you can make a decision. Yeah, so that more or less sums up the 3 weeks of the roadmap for AI. And yeah, I'd just like to open up to the floor if you all have anything to add on before I end the session.
Yeah, I just have one last question. So when you had a slide with multiple environments, right, or multiple layers.
Yeah,
One was like the skiing place and
yeah, this one.
right. So these multiple populations, so they're the foundation of what you were talking about, to creating multiple models, right? So are these multiple populations, are they separate or they can be connected?
They are usually separate because you are just trying to imagine like multiple futures in the population. But of course, if you are talking about world modeling, like basically not world modeling, like you are talking about multi-population modeling, like all these populations form an ecosystem. You want to model the entire ecosystem, then these multiple populations can interact with one another. So it depends on the scale you want to model. I just stopped at multiple populations because if I go any further, it will be like multiple Earths, multiple galaxies, and so on. Then there's no end to this. So I just stopped at multiple populations.
So this can be applied, say, for example, in the case of like NVIDIA, they have like simulations and they can actually simulate a factory. So in this case, it can be like multiple factories and multiple companies, and they all have that. Okay, got you.
Yes, but in this slide, what I was referring to is we'll simulate multiple slices of what might happen for each population. So what you're describing, like the factories and so on, you can imagine them to be like, you just increase the scope of your simulation here to include multiple factories. Yeah, but I'm talking about like you simulate different possibilities of what these multiple factories could be. So that's the key idea of this slide. Yeah.
Got you. Great.
Yeah, if not, that's a great discussion. I think this whole topic on how to achieve singularity is a very important one. I don't think we'll ever hit the singularity, but the idea of how we can use agents, multi-agents, memory, even goal-directed learning from experience of one another, all this will help to shape how AGI and ASI can be achieved. And I think this is quite important. And to just conclude, if let's say we ever want to have a poster image for artificial superintelligence, I believe the multiple sampling and filtering is quite an important one. And so this Doctor Strange image is actually one of the most apt images for ASI. So yeah, if anyone wants to adopt this image for ASI, feel free. So this is what I think is the most appropriate in my own opinion. And so, yeah, I'd like to end the presentation now. And thanks so much for coming. I'll see you all again next week. Okay, bye.
Okay, thank you. Great job. Thank you.